Hello, and welcome to this presentation on the new features in Mascot Server 2.7. My name is Richard Jacob, and I'm the Country Manager for North America. The big new feature support for Mascot 2.7 is Crosslinking. This and the Quantitation Summaries feature and improvements to how we search for modifications are covered in separate talks. In this talk, I will cover the following topics: protein false discovery rate, fragment charge states, better filtering of modifications with complementary deltas in an error-tolerant search, combined search results in Mascot Daemon, MGF exporting spectra in the original order, and handling non-standard modification names in spectral libraries. We've added full support for a comprehensive range of cross-linking scenarios. This includes editors for the cross-linking agents and methods, fragmentation patterns in peptide view, and exports to XI view for further visualization. Mascot can report all the different types of links, from looped, inter, and intralinks, and incomplete monolinks. Mascot Server 2.7 has better site localization by introducing separate caps on the number of distinct modifications in a peptide sequence match, the number of modified sites in a PSM, and the total number of arrangements to be tested. Mascot Server 2.6 worked well but had limitations. If a peptide had less than 16 possible variable modification permutations, then there are no issues as all possibilities are tested. It's in the cases where the peptide has more than 16 possible permutations that issues can arise. The sliding window method tends to cluster modifications on adjacent modifiable sites, and it will often stop before 16 different permutations have been tested. In Mascot 2.7, we've taken a different approach. We use a single, consistent permutation method. There's no switching between different methods. The new permutation iterator samples arrangements using a uniformly random scheme. The operation of this is controlled by 3 user-definable settings. By adjusting the parameters, you can choose to reduce the search depth and speed up searches of lightly modified samples, or increase the search depth where site localization matters, or for highly modified samples. The Quantitation Summaries feature in Mascot Daemon allows you to select one or more tasks and create a sample map. The sample map is used to annotate the list of results files with recognizable sample identifiers. And Daemon creates and saves the Quantitation Summary, a tab-delimited text file which is the input file for statistical analysis. This can then be used with anything from Excel to Perseus or a programming environment like R. Go and see the presentation if you would like to see the examples of what you can do with the output. If you would like to know more about cross-linking or the changes to modification detection, check out those respective presentations as well. The new protein false discovery rate value is automatically calculated when the decoy search option is selected. It is displayed above the peptide PSM decoy results. Protein FDR is based on the following assumptions and definitions. By default, the protein family report only shows peptide sequence matches, PSMs, with significant scores and are used for the protein family assignment. A protein family member may represent multiple same-set proteins. Only members of all the protein families in the report, those that contain a unique peptide, are counted. Protein count used for FDR is a count of family members. That is, if the report contains 2 families, one with 4 members and the other with a single member, this counts as a total of 5 proteins. Same-set, subset, and intersection proteins are not counted. While a protein ID is a false positive when all PSMs are false positives, just one true PSM would make the protein identification a true positive. This is very important. Given the number of proteins and the number of true and false peptide sequences, We use a hypergeometric model to estimate the number of proteins that are truly false positive. The algorithm is a simplified approach to that used by Mayu from the Aebersold group. The main differences are that we do not make a separate estimate for the FDR for one-hit wonders, and we do not partition the database by protein size. We use a simpler estimate for the number of false proteins in the target database based on the assumption that the number of decoy proteins never reaches a significant proportion of the database size. Imagine the target database has 1,000 entries and the search results show 500 target proteins and 10 decoy proteins. Does this mean protein FDR is 10 divided by 500 or 2%? No, it does not. We can assume the false peptide sequence matches in the target are distributed across 10 proteins, but some of these will also contain true peptide sequence matches, so should not be counted as false. Since half of the proteins in the target database contain true PSMs, a reasonable estimate would be that only 5 target proteins contain nothing but false peptide sequence matches, so that the protein false discovery rate is 5 over 500, or 1%. The default significance threshold for a Mascot search is usually 0.05, and this will often give a peptide false discovery rate in the region of 5%. In this dataset, the protein FDR is approximately 4.5%. If we want to lower the protein FDR, we can try adjusting the peptide FDR to 1%. In this case, the default peptide FDR is already close to 1%, so we can try adjusting the report other ways. We can adjust the minimum number of significant unique sequences. This has quite a strong effect on the protein FDR. If we change it to 2 and eliminate the one-hit wonders, the protein FDR drops to about 0.18%. Alternatively, we can adjust the significance threshold for the results. I took a guess and reduced it by a factor of 10 from the default values of 0.05 to 0.005 and clicked the Format button. The resulting protein FDR is approximately 1%. The current HUPO interpretation guidelines for large-scale results recommend adjusting the setting to lower than 1% protein level global false discovery rate. So, after formatting, this search result would meet those guidelines. When interpreting the results, a protein FDR of 1% only tells us that 1% of the proteins listed are wholly false. This doesn't mean the other 99% are correct. Particularly, when there are same-set proteins, we cannot say which one is correct. This is because database redundancy causes protein inference ambiguity, and we can account for the PSM evidence using several sets of proteins. It is important to remember that a protein accession number in the summary report does not mean this is the correct protein. It means the correct protein is likely to be very similar to one of the set of proteins represented by this family member. Mascot Server automatically searches for fragment ions as singly or doubly charged ions, but not higher charge states. Middle and top-down analysis of large peptides and proteins can generate fragment ions with charge states of 3+ or higher. In the past, if you have fragment ions with higher charge states, you need to deconvolute them to MH+. This is supported by Mascot Distiller and is still the preferred method. For software that does not decharge the peaks, we added support for specifying the charge state in the third column of the peak list. So you have mass, intensity or area, and now charge state. Any data in the latter columns will be ignored. The new feature is on by default and controlled by the Decharge Fragment Peaks configuration option. Decharge Fragment Peak is the maximum absolute charge state to be decharged and is set to 10 by default. As we expect all the fragment ions in the peak list to be MH+, there is no need to search for 2+ ions. To improve the specificity of the search, we recommend creating an instrument configuration that removes support for 2+ ion series. The next feature is better filtering of modifications with complementary deltas in error-tolerant searches. Error-tolerant search results automatically remove matches where the delta of the modification is less than the smaller of the precursor or fragment ion tolerances. For example, Q to K in most cases. In Mascot Server 2.7, we extended that filtering to remove matches with pairs of modifications where the deltas sum to 0 within the precursor tolerance. Such matches allow the fragment masses to be shuffled around to get a better score while leaving the parent mass unchanged. These are almost always false, with the true match without either mod getting a slightly lower score. Some examples of this are asparagine to glycine and glutamine to alanine are exact inversions of carbanoidomethyl. A combination of deoxy and cyranine to alanine or deoxy and tyrosine to phenylalanine are exact inversions of oxidation. Here I show the reporting of a peptide with a carbanoidomethylation at the N-terminal and an equivalent loss of 57 Daltons asparagine to glycine modification at the asparagine 5 position. Expanding the top 10 matches of the peptide shows the unmodified peptide with a significant score 6th on the list. In Mascot Server 2.7, all of the top 5 matches have been filtered out and the bottom 4 too, leaving just the unmodified sequence match. We added a new feature to Mascot Daemon which allows you to easily combine search results. When working with fractionated samples, you will want to combine the searches from multiple data files into a single result. The easy way to do this is with the Merge MSMS files into single search option in Mascot Daemon. However, if you are using the Windows operating system for your Mascot server and the default IIS web server, you can hit a 4 GB upload limit. There are a number of ways around this limit, such as using Mascot Daemon on the same computer as Mascot Server, so the searches are submitted on the command line, or moving from the IIS web server to Apache, or using Mascot Distiller for peak picking and merging the results there. These are described in an older talk from 2015. Now, Mascot Daemon 2.7 gives you another way to merge searches. This is useful when users are using MS-Convert or other peak picking third-party tools and not using the merging features of Mascot Distiller. Instead, you can select multiple searches in a Mascot Daemon task by control-clicking individual searches or shift-click Arrange, then right-click and choose Combined Report. The combined search will open in a web page and list the results files that have been merged at the top of the report. This will work with searches that have been processed by any peak picking software, including Mascot Distiller. This next feature requires some background. When a peak list is submitted to Mascot, the neutral molecular mass, MR, is calculated for each precursor and queries are sorted lowest to highest. The precursors are given a new index number based on this sorting. You can run into a problem related to the change in order of the precursors in an MGF file when using search results with third-party analysis software. When generating an MZ-ident-ML file from the Mascot Server search results, the spectrum IDs field in the MZ-ident-ML file refer to the original MGF file precursor order. Some third-party analysis software, such as the PRIDE submission tool, maps the data in the MGF file to the data in the MZ-ident-ML file. If a collaborator exports the search results from Mascot but does not have access to the original MGF file, they can export it from the search results too. In Mascot Server 2.6, the newly created MGF file is exported in the sorted order of the precursors, not the original order. The mapping between the mz-ident.ml file and the MGF file will fail, and the collaborator is left thinking that either Mascot Server or the third-party tool is broken. To prevent this misunderstanding, the MGF file can now be exported with the precursors in the original order to maintain mapping compatibility. To put the new feature to use, go to the export menu, choose MGF peak list, and it is the default option. In 2008, the Proteomics Standards Initiative released community standards for representation of protein modification data by use of a consensus nomenclature. Prior to that, there were some differences in modification names between search engines and research groups. Also, some of the old names or acronyms did not meet the new guidelines. Some of the modifications had a common name, but it did not conform to the new standards. For example, sodiated, which now equals cation Na, or used lab acronyms CAM, which equals carbidoidomethyl. These names live on in old datasets, some of which have been used to create spectral libraries that are publicly available from NIST. Mascot Server could not match these modification names to the newer ones and would report an error for those spectra, effectively excluding them from the library. To fix this, we have introduced an alias file that maps the old names onto the new names. The alias file resides in the mascot config directory and is pre-configured with 46 common aliases and acronyms. It is extendable as well. So that brings me to the end of this presentation on the new features in Mascot Server 2.7. If you are interested in the first three features, crosslinking, modifications, and Mascot Daemon sample maps, please have a look at those presentations separately. Thank you for attending the virtual ASMS, and we hope to see you next year.